The fastest star in the Milky Way. We are widely aware that planets revolve around their host stars. Depending on how far they are from the star, some of them go faster than others. In its orbit around the Sun, Jupiter, for instance, moves at an average speed of 13.7 kilometers per hour compared to the Earth's 29.78 kilometers per hour. But have you ever wondered what a star's typical velocity is? Stars can differ greatly from one another, even though they are less diverse than planets. Some of them are dwarfs, while others are giants, because the gas they are comprised of has a low density. Some of them are quite dense, while others have a large radius. So, how can we calculate a star's velocity? To find out the answers to these questions and to learn more about the Milky Way's quickest star, keep watching this video. Spoiler, it goes faster than you can imagine. The Milky Way's quickest star that recently discovered moves swiftly at 8% the speed of light. This indicates that its average speed is roughly 24.000 kilometers per second, or 15.000 miles per hour. To make this video less dull, we will henceforth refer to the star as Bolt, even though its official name is S4714. Bolt manages to survive in the harsh conditions in the galactic nucleus. It is in orbit around Sagittarius A star, the Milky Way's supermassive black hole, which is an odd and peculiar object. As we previously stated, it travels at a speed that is 8% of the speed of light, but what if I told you that this is not even the most remarkable aspect about it? Bolt is actually a strange kind of star called a squeezer. Astrophysicists Tal Alexander and Mark Morris first postulated squeezers-type stars 20 years ago. They proposed the existence of a class of transient sources called squeezers, which are stars caught in highly eccentric orbits around a massive black hole and whose unusually high luminosity is powered by tidal interactions with the black hole, in an article they published on the Astrophysical Journey. They exist because the galactic center contains a supermassive black hole, a mass sink that propels a flux of stars into almost radial orbits to replace those it has destroyed. So, the first contenders for a type of star that was initially postulated approximately 20 years ago have been provided by our star, Bolt. In other terms, squeezers are stars that approach black holes so closely that they are squeezed by the tidal forces of the black hole. Bolt is merely one of several stars that have recently been identified as skimming Sagittarius A star on orbits that are closer together than those of any other stars previously identified. The environment around Sagittarius A star can be quite chaotic, despite the fact that the Milky Way is a relatively quiet galaxy in comparison to other, more active galaxies with quasars in their centers. Well, there is a bulge there. The black hole is always surrounded by stars orbiting it in peculiar ways. For instance, astronomers have discovered several stars in that region with looping, protracted, and severely elliptical orbits. Simply see the journey as an ellipse with a black hole at its center. These trajectory choices are absurd. You have the recipe for the most bizarre kinematics discoveries we can make in our universe when you add the fact that they move along their courses at an incredible velocity at some percentage of the speed of light. Isn't it incredible? These bizarre moving stars are known as S-stars, and we may use them to investigate the characteristics of the enormous invisible object they orbit. For many years prior to Bolt's discovery, S2 was thought to be the closest star to the black hole. The gravitational boost from the approaching black hole can accelerate this star to 3% the speed of light at its periapse, or the point at which it has reached its greatest velocity. Afterwards, though, a group from the University of Cologne in Germany discovered another star, S62, which was much fainter and hence more difficult to see. Sagittarius A* took 9.9 years to orbit the Sun. That is closer than Uranus' typical separation from the Sun. However, because of its proximity to the black hole, it must have moved far faster than S2. In fact, astronomers calculated that it might travel at a maximum rate of 6.7% the speed of light. But Peisker, the team's principal author, wasn't finished. After many years of research, the team has now identified 5 other S stars that are even closer than S2, S4711, S4712, S4713, our Bolt, and S4715. I am glad that I got the opportunity to work with and view the Galactic Center with a very large telescope over the last 7 years, Peisker said. S4711 and S4714 are the 2 most significant of the new stars. Let's review our knowledge on S4711. With a periapse distance of 21.5 billion kilometers, we know it is a blue B-type star that is 150 million years old and orbits Sagittarius A** once every 7.6 years. Because its period of 7.6 years is less than S62's, we can infer that it has the closest mean distance to the black hole of any known orbital object. In contrast, S4714, Bolt, has an orbit that is much more eccentric than S4711 but has a longer orbital period, 12 years. Eccentricity, which ranges from 0 to 1, is a metric for how round an orbit is. A perfect circumference corresponds to 0 eccentricity. An ellipse with a large eccentricity is lengthy, with a value of 1 being an escape orbit. The orbital eccentricity of S4714 is 0.985. According to Peisker, these extreme stars are the first actual candidates for squeezers, which were first theorized in 2003. A class of stars with extremely eccentric orbits around powerful black holes was hypothesized by astronomers Tal Alexander and Mark Morris. A portion of the star's close orbital energy is converted into heat at each pass by the tidal forces. In addition to making the star shine brighter than it would otherwise, this also has an impact on the orbital decay of the star. Squeezers are therefore orbiting dead stars. At least S4711 and S4714 are squeezer possibilities, claims Peisker. As the orbital elements agree with Tal Alexander's estimates from 2003, I would conclude that I am confident about S4711. S4711 is the first squeezer ever discovered in this way. If confirmed, these stars could fundamentally alter how we think about how black holes interact with the stars they eat. Stellar kinematics played a significant role in each of these studies. What is it then? And why is studying stellar kinematics important? To help us continue to develop and make these videos better for you, the viewer, please make sure you like or dislike the video before responding to this question. Stellar kinematics is the observational study or measurement of the kinematics or motions of stars across space in astronomy, as one might expect. Stellar kinematics includes the internal kinematics of more distant galaxies as well as the measurement of star velocities in the Milky Way and its satellites. The kinematics of stars in various parts of the Milky Way, including as the bulge, the thin disk, the thick disk, and the stellar halo, may be measured. This information is crucial for understanding the genesis and development of our galaxy. Kinematic measurements can also spot unusual occurrences like hypervelocity stars erupting from the Milky Way, which are thought to be caused by binary stars colliding with the supermassive black hole at the center of the galaxy. Stellar dynamics, which deals with the theoretical study or modeling of the motions of stars under the effect of gravity, is related to but different from the field of stellar kinematics. To study the evolutionary history and mass distributions of systems like galaxies or star clusters, as well as to find the presence of dark matter or supermassive black holes through their gravitational influence on stellar orbits, stellar dynamical models of these systems are frequently compared with or tested against stellar kinematic data. Now that we have said that, we can use kinematics to put our theories to the test. For instance, we can utilize these stars to test general relativity since they approach relativistic velocities. In some of the most difficult experiments yet, the star's light stretching as it approaches the black hole and the way its orbit changes like a spirograph supported Einstein's hypothesis. You're probably wondering if it's feasible to locate stars circling Sagittarius A star that are moving at even faster speeds. This is certainly a possibility. We ought to be able to locate them with the introduction of more potent telescopes in the upcoming years, such as the Very Large Telescope. Just be patient and continue to keep it intrigued, as always. Here's where the video ends. Thank you everybody for watching. What are your thoughts on this video? Do you think we will spot faster stars in the upcoming years? Tell us in the comment section below, and see you on the channel again soon.